Right, crazy experiment, I know, but if I roll a marble down here, it goes an imprecise distance because this is a rough slope and it's going across a rough carpet, so they don't all go the same distance. But I'm going to collect some data to show how far these marbles have rolled, and to help me I've put a piece of cotton here 45 centimetres from the end of the track so that I can measure exactly how far each marble has gone. So this marble here has gone 45 plus 7.2, so it's gone 52.2 centimetres, whereas this one here has only gone, take off 1.8, so 43.2 centimetres. And I'm going to collect this data for a whole lot of marbles. Right, well, I've rolled my 20 marbles and I've used my trusty ruler, my clipboard, and these are my results. So I've got here the results, and the shortest one was 39.3 centimetres and the longest over here 62.3. Most of them travelled sort of between 55 and 60 centimetres. But if you look at the marbles, you see there are slightly different sizes, so they've got slightly different masses, and therefore they would travel and respond to the bumps in a different way. I want to collect this information together and present it as a histogram. Hello, sorry about my classroom here. 3 rather vacant looking dolls and a Lego sheep. Perhaps it's familiar. Why a histogram for our marble rolling data? Well, there are a number of good reasons. Firstly, the data was continuous. We didn't get exact values of centimetres because we were able to measure quite accurately. You had decimal parts. So any data which is measured like that, so can actually take any value within a certain range, is called continuous data, and the best way to describe that is in a histogram. We're grouping the data together. We won't get many repeats. So if you tried a bar chart, you wouldn't find any values repeated, so it would just be a long horizontal strip of ones. The good thing about the histogram, it will show the spread of the data. So all the way from that 39.3 up to the 62.3, which was the longest roll of a marble. But it will also show in the high point of the diagram what the typical values are. So you'd be able to say that typically a marble rolling down a 10 centimetre track across carpet might travel about 55 centimetres perhaps. Right, so I've collected my data and I've put it all in order down here because it helps to organise things. And now I need to group it together, so I need some class widths. And it helps if my class widths are nice values which divide well, so things like 10 and 5 and 4, rather than numbers like 3, 6 and 7 which leave long horrible decimals. So if I go from 39 to 49 and 49 to 54 and to 59 and then to 63, my class widths are 10, 5, 5 and 4. And that should help me collect the data and get some nice values. Well, I'm sure you've been wondering, why was the sheep here? Well, for a histogram we need something, a unit of area, and for this the sheep has brought some wool. Well, Lego wool. Each one piece of wool represents one piece of data in our histogram. So I'm going to do this in Lego. This is my scale. It's a continuous scale. So this is the 35 to 40, 40 to 50, 50 to 60 and 60 to 65, and I put little markers at 39 and 49, 54 and so on, because a histogram is really a whole lot of little trays, and you're going to stack data in those trays, and then you're going to heat them up so they melt, so that it's the area that makes the difference. Now, to represent my bits of data, I've got Lego bricks, so I need to go through the data and assign it to the right group. So I had 39.3, which is in 39 to 49. Then I had 43.2 and 48.5, so they're all spread there. Then we had from 49 to 54, well, there's 51.8 and 52.2, so I've got those two bits of data. And the next group, which goes from 54 all the way up to 59, needs 54.1, 54.6, we've got 55, 55.5, 56.2, 56.8, 57.3 and 58.9. Well, it really helps if I can sort of start stacking these up, because there are really too many of them to fit into that group, aren't there? So maybe I should stack them like that. And lastly, we've got 7 more bits of data. So there's a 60.6, a 60.7, and we had a 60.8, and a 60.9, and we have a 61.4 and a 61.5, and finally the superbly large value of 62.3. So there's my data, and this is really what a histogram is, basically. But we don't want to have the data spread out, we want it melted so it fills a rectangle which has got the same area as these 3 pieces. That's what we're going to do with our calculations in just a moment. So this class here has a width of 10, but it's only got 3 bits of data in it. So I really need to divide the 3 by 10, so I need an average height here of about 0.3. This class has a width of 5. It's got 2 bits of data in it, so 2 divided by 5 would make an average height of 0.4. But this class, 5 wide, has got 8 bits of data in it. That would be 8 divided by 5, 1.6 should be the average height of this group. And this one only has a width of 4, it's got 7 bits of data in it. And I'm sure you can work out that last calculation, 7 divided by 4, 1.75. So ideally I should have rectangles here, because a histogram shows frequency by the area of each rectangle. Well, I'm sure that some of you would rather not make a histogram out of Lego, so this is how to do the calculations, and then I shall show you how to draw it. Firstly, I've listed all the data here and I've put it in order, and I've totaled, so these are the totals, if you like, subtotals for the classes that I spoke about earlier. And these totals I've listed down here in as the frequencies. Now, in a histogram, frequency is represented by area, which is why at the top of this column there is the title area. We now need to work out the width and the height for the rectangles to make this histogram. So let's look first of all at how we do the widths. To find this width for the first class, I need to do 49 and take away 39. So I need to take the lower class boundary, 39, away from the upper class boundary of 49. And that calculation gives me 10. If I do the same thing with the other classes, I get 5, 5, and 4. And then we come to the heights. Well, you'll recall that they were rectangles for a histogram, So I need to work out what height would you need to have an area of 3 and a width of 10. Well, the height would need to be 0.3. How did we get that? Well, we divided the 3 by the 10. So if I do similar calculations for the other classes, I'll just do the next one. So I need to do 2 divided by the class width for this column here, and I'm going to get a height of 0.4. The other two heights are 1.6 and 1.75. I'll let you check whether or not those are correct. Now, a histogram is a scale diagram, so I need a scale along the bottom. And onto this scale I need to put the class boundaries. So we had about here 39, and then we had 49 and 54 and 59, and about there 63. So these are important values and they need to be written quite clearly on your scale. So there I've written them. Those are the class boundaries. And into these boundaries we were putting Lego bricks, pieces of data, and we were then wishing to compress that data to form rectangles. So this first rectangle here, which is not a very well drawn rectangle, represents the 3 pieces of data which were in that group from 39 to 49. So this rectangle needs to have a height of 0.3. So I'm going to write 0.3 at the top. It's a scale diagram in both directions. So the next rectangle needs to be very slightly higher, 0.4. So it might really help if I put up here a vertical scale. Now if you look where I've written height at the top up here, beneath it I've written frequency density, and that needs to be the title or the label for the vertical axis. And it's a nice scale which is constant, so that would be about 1. Here will be about 0.5. So you can see that my 0.3 and 0.4 would fit in. But at the moment this diagram's a bit scrappy, so perhaps I should have a better go. So here is my tidied up diagram. I've got a nice vertical scale which has been drawn with a ruler. I've got some rectangles which have also been ruler drawn. And I have written above each rectangle its height. It makes it much easier to read. And to summarize, this diagram now shows us that the most common distances rolled by the marbles were around here, say between 54 and 63. You could say that the modal group, which is the one with the highest height, so the greatest frequency density, the modal class is 59 to 63. So to summarize, why is a histogram a good diagram? Well, if you look at the diagram at the top here, it's quite quick at a glance to see that most of the marbles travelled more than 54 centimetres. There were just a handful that travelled less down here, 39 to 54 centimetres. But you can see that at a glance, and that's why a histogram is such a powerful diagram. It communicates through the shape. I can judge, perhaps only by eye, that the marbles that travelled the greatest distance, the top end, I could see that maybe the average of those is 58 or 59 centimetres that they travelled. So if I were to roll another marble down that slope, that's how far I'd expect it to roll, about 58, 59 centimetres. On the right hand side, I've listed the steps that you should proceed through in order to complete a histogram. So collect the data, choose class boundaries, and then group the data according to those class boundaries, and then use a table to organise that data. It lines up the figures so the calculations are easier to do. Calculate those rectangle heights, and then carefully illustrate those rectangles by making sure they have the correct width and the correct height, and put them on a scale so that you have a diagram which is proportional. And that's really all there is to making a histogram.